So in this chapter, chapter 4.2, Exponential Functions, we're going to graph exponential functions. We're going to evaluate exponential functions. And we're going to look at the use of exponential functions to compute compound interest, and we're going to use exponential functions in applications. Our first objective is the definition of an exponential function. Let b be a constant real number such that b is greater than 0 and b does not equal 1. Then for any real number x, a function of the form f of x equals b raised to the x is called the exponential function. Notice that in the past we've looked at the variable raised to a number, to a power. So for example, we had y is equal to x squared, or we had y is equal to x cubed minus 1. Now we have a number raised to a variable, which is now an exponential. So in this case, we may have y is equal to x raised to the x power, or y is equal to 3 raised to the x minus 1 power. Our first objective is to actually look at how to graph exponentials. So in our first example, we're going to write out the numbers for x and f of x, and then we're going to plot them and see how the graph works. So we're going to start with the first number, 0. So when x is 0, we have 3 raised to the 0 power, and we notice from previous experience that anything raised to the 0 power is just 1. So if we had 1, if x is 1, we have 3. If x is minus 1, now we have x raised to the negative 1, which is 1/3. X raised to the second power is 9. Raised to the minus 2 power is now 1/9. And you can start seeing how this goes. If this is 3, we get 27. And if it's a minus 3, we get 1/27. So now if we graph this, we will start out at the point where x is 0. When x is 0, the function is at 1. Now we ask ourselves, what's happening to the function as x becomes more negative? Well, it's getting closer to the x-axis. And in fact, we can consider this x-axis as a kind of horizontal asymptote. So as it gets closer, as it goes further negative, this function gets closer and closer and closer to 0, right? Now, as you can see, when x is at 2, we're at 9. So 2, 4, 6, 8, 9, we're right up here at 2. At 1, we're at 3. So at 3, we're here. So you can see now that this function goes like this very fast. So there's our function. Now we're going to graph f of x is equal to 2 to the minus x. So now we see that if x is 0, we still have f of x is at 1. When x is 1, now we have 2 raised to the negative 1 power, which is now 1/2. When x is negative 1, we have 2. When x is 2, we have f of x is 1/4. When x is negative 2, we have x is 4, and when we have x is 3, you can see that this is 1/8. When x is minus 3, it is 8. So again, we're along the horizontal axis that we're going to get closer and closer to 0, but this time, when we go to the point at 0, 1, which is our point that we move from positive numbers to negative numbers, or vice versa, we can see that as x gets larger, we get a number that's closer to 0. When x is, say for example, negative 1, actually I have a mistake here because my points are really at right here at 1, so I'm really like this, right? As x becomes, now I have 2, and at negative 2 I'm at 4, and at 3, negative 3, I'm at 2, 4, 6, 8. I'm already up here, right? So this thing is moving in this direction. So there is my function, and you will notice that this function, if I have a negative power, now I see that the function is just switched. The function becomes going to infinity on the negative side of x versus when it's 2 of x. So now we have things just a little bit more complicated. We have f of x is equal to 1 minus 2 raised to the x plus 1. Well, the first thing we notice is this negative 2x plus 1. If this number becomes much more, if the power becomes much more negative, then negative 2 raised to the x plus 1 becomes very, very small. And so essentially what happens is we have a horizontal asymptote at 1. So I'm going to mark that 1 in. Okay? We'll never cross over a positive 1. So let's do some of our calculations. Let's let x equal 0. When x is 0, I have 1 minus 2 raised to the 1 power, which is a negative 1. So now I'll let x equal 1. If x is equal to 1, I have 2 minus 2 raised to the second power, which is a negative 4, but 1 minus 4 is a minus 3. Suppose I have a negative 1. So now I have 1 minus 2 raised to the 1 plus 1, which is 0. So now I have 1 minus 1, which is 0. If I have 2, I have 1 minus 8, right, which is a negative 7. If I have a minus 2, right, if I have a minus 2, I have 2 raised to the negative 2 plus 1, which is a negative 1. So 2 raised to the negative 1 is 1/2. So I have a 1/2, right? And so we can see with 3, I'm going to get 3 plus 1, which is 4, and 2 raised to the 4th power is a negative 16. So this is going to be a negative 15, right? But a negative 3 is going to be a negative 2, so a negative 2 raised to the negative 2 power is a negative 1/4, so this is going to be 3/4. So I'm getting closer to 1, but do I ever get there? The answer is no. So now we can just plug in some of our points. We have a point here at 0, 1. We have, negative 1, 0. We have a point at negative 1, 0 as well. And we can also look at negative 2, 7, or positive 2, 7. So this is when x is 1, we're at negative 3. Oh, yeah. When we're at negative 1, we're at 3. 1. So this is at, I think we have our points again wrong. So this should be here. And at 1, we're at 3 here. And then at 2, we're at 7, which is 2, 4, 6, 7 is about right here. So the way this goes is like this. So we're kind of going in this direction. So there's our function right there. So in this case, it says use transformation to graph functions. One of the ideas that you have to look at is whether you're adding or you're subtracting from the exponential part of the function, which is this part of the function is exponential. If you're adding or you're subtracting, you're either going to shift up or you're going to shift down. Notice that, however, as the exponential function gets smaller in a particular direction, it gets closer and closer to k. So wherever k is going to end up being your horizontal asymptote as the exponent gets smaller, forces the exponent to get smaller and smaller and smaller. So for example, if we started out with the parent function, y is equal to 2 raised to the x, we knew what that function looked like. For example, that function started out looking at 1, when 1 is at 2 is at 4, this is at 8, 2, 4, 6, 8. So now this part of this function, essentially this is f of x equals 2 raised to the x power, right? So let's write that out, 2 raised to the x power. So that's the parent function. Now we notice in the new function, f of x is equal to 1 minus 2 raised to the x plus 1. We know that k is either shifting up or down, right? So in this case, k is shifting upward. But now k actually, in this case, is this vertical asymptote that we're going to approach as the exponent part, this part here, gets smaller and smaller and smaller. We know where that's going to be at. So we know 2 points that are very close. When x is at a minus 1, we know the function crosses right here at negative 1, 0. We also know that when x is 0, we're at a negative 1 here, right? So now the new function is going to look very much like this because it's going to approach 1 coming from this way. So this function we can just look at, we can just do the y and x intercepts, and we can see how this function is going to be manipulated by this particular asymptote. We can see that it can't cross that asymptote. So there are the two functions, the parent function and the new function f of x equals 1 minus 2 raised to the x plus 1. So now it's your turn. I would like you to try to graph g of x is equal to 2 raised to the x plus 2 minus 1. So you will notice in this particular case I looked at letting x equal 0. When x is equal to 0, we have g of x is equal to 3. So we put 3 in, and then we set g of x equal to 0, and we solve, and we find that x is equal to a minus 2. And then we graph, and we see that this function gets closer and closer to a minus 1, but it never quite gets there. So in this particular section, we're going to evaluate the exponential function based on e. E is a universal constant like the number pi and an irrational number. As x approaches infinity, the expression 1 plus 1 over x to the x approaches a constant value that we call e. E is approximately 2.718281828. So in examples 4 through 7, we're going to actually look at e round to 4 decimal places. So for example, e squared is approximately equal to 7.3891. E to the minus 3, if you did this on your calculator, would give you 0.0498. Please try this on your calculator. E raised to the square root of 7 is approximately equal to 14.0940, and then e raised to the pi is approximately equal to 23.1407. So in this particular example, we're going to look at f of x is equal to xe raised to the x plus 1. So we're going to find out what x is, and we're just going to look at both the situation when x is 0. So when x is 0, we have f of x is just equal to e raised to the 1 power, which in this case is just 2.718. So the other issue is we're going to let x equal minus 1, and this is e to the 0 power, which guess what, is just 1. Now if we let x equal 1, we have e to the 2 power, and in this particular case e to the 2 power is 7.389, and if we go e to the minus 2 power, we get e to the minus 1. If we get e to the second power, we get e to the 3. in both of those cases, e to the minus 2 power is, well, minus 2, which is a minus 1 actually, is 0.367. And then when we put a 2 there, we get e to the third power, and that is 20.08. So you can see how the numbers are actually working. If we look at the numbers, the two major numbers that we're going to look at is when x is minus 1, we're at 1. And so in this case, we're right here. When x is 0, we're at approximately 2.7, almost 3. So we're right about here. So now you can see what happens immediately. When x is 1, we're already at 7. So there's 2, 4, 6. We're almost at 7.38. So this one, again, we're getting closer to the 0 here, and then we're moving up in this direction here. So that's how we're going to graph this function. So we use exponential functions to compute compound interest. Suppose that $P in principal is invested or borrowed at an annual interest rate R for T years, then I equals PRT. And we've seen this in the past in some of our examples at the beginning of our class this semester. But now we can add in compounding. So when we look at compounding for periods, we can look at the amount that's in the account is equal to the principal times 1 plus the rate of interest divided by the period of compounding raised to the compounding period times the time in years. And so that's our major compounding formula for interest and the amount left in the interest. The other formula is compounding continuously, and in that case we're using P is equal to R T. P is equal to E raised to the RT. So here's our first example. Suppose that 15,000 is invested with 2.5% interest under the following compounding options. Determine the amount in the account at the end of 7 years for each option, compounded annually. So we can write out the formula immediately. We know that it's the A is equal to P1 plus the rate over N and T, and in this case the amount compounded annually is just P times 1 plus 0.025 divided by 1 times 1 times 7 years. So A is equal to 1500, 15,000 that is, times 0.025, we got to watch that, raised to the 7th power, and that ultimately equals the result. If you did this on your calculator, you would get this amount here. And it's an approximation. We raise it up to that point. Now we're going to compound quarterly. That means that N is equal to 4. So using the same formula, A is equal to 15,000. And it's 1 plus 0.025 divided by 4 raised to the 4 times 7. So A is equal to 15,000. 1.00625 raised to the 28th power, and that's going to give us 17,858.96. Now suppose that 15,000 is invested with 2.5% interest under the following compounding option. Determine the amount in the account at the end of 7 years for each of the options. Well, now we're going to look at compounded continuously. Here, the amount is equal to P raised to the RT. So the amount is equal to 15,000 e to the 0.025 times 7. So when we do it on our calculator, we get approximately 17,868.69. In example 10, a weapon-grade plutonium is composed of approximately 93% plutonium. The half-life of plutonium-239 is 24,000 years. In the sample originally containing a half a kilogram, the amount left after T years is given by the amount in times in T years is equal to 0.5 kilograms times 1/2 T raised to the 24,000. T divided by 24,000. It says evaluate the function for the given value of T and interpret the meaning in context. So at the amount after 24,000 years is just going to be equal to 0.5 times 1/2 raised to the 24,000 divided by 24,000, and that's just 1, right? So that's just equal to 0.5 times 0.5 on your calculator raised to the 1 power. And guess what? That is 1/4 kilograms that we have left after 24,000 years. So now, after 72,000 years, we have 0.5 raised to the 1/2 raised to 72,000 divided by 24,000. That's equal to 0.5 times 0.5 raised. In this particular case, when we raised it, we got actually, we raised it to, I think, the third, right? There's 3. And when we do it on our calculator, we get approximately 0.0625 kilograms.
Honey? Mommy went to the store. Oh, well, you see,
In our last example, a 2010 estimate of the population of Mexico is 111 million people with a projected growth rate of 0.994% per year. At this rate, the population PT in millions can be approximated by the formula P of T is equal to 111 times 1.00994 raised to the T, where T is the time in years since 2010. It says evaluate P of 4 and interpret the meaning in the context of this problem. So P of 4 is really what's the population of Mexico in 2014. So to look at P of T P of 4, in this case, it's going to be 111, 1.00994 raised to the 4th power. And in this particular case, when we did it on our calculator, we got approximately 115.479 million, right? So that's in millions of folks. Now when we do it with P75, you should do this on your calculator. And when you do it on your calculator, you should get approximately 233.07 million people. So these are some of the applications that we use using exponentials. Please study the problems in the chapter of 4.2 and also try the problems of the day.